Variation is one of my more favorite topics in this course. And I always like to end, after you learn how to do all these calculations, I always like to end with some discussions of what insights it can provide to us. And so I want to talk a few minutes about a little bit of mathematical biology and maybe a few other things. And so you might think in the natural world there are basically three kinds of dimensions. There's the length dimension, there's the area dimension, and then there's the volume dimension. And now you encounter other things in the physical world. For example, a pendulum, the time it takes for a pendulum to swing back and forth varies directly to the square root of the length. So you can have like a square root involved. But those are a little rare. Most of these variation problems involve first, second, and third powers, directly, inversely, jointly combined, all that stuff. Let's take some simple examples from the biological world. How come insects don't get bigger than they do? You know, when I was a kid watching these old bee movies, they were called. A bee movie was a movie that was made very cheaply. Was usually kind of cheesy and used unknown actors because they could pay them real cheap. And so they made a lot of these movies in the 1950s, and I used to watch them on the reruns on Friday nights as a kid. And occasionally there'd be a nuclear accident in these movies, and you see 6-foot long ants terrorizing people, things like that, things that had mutated to enormous size. Really, that's all quite impossible. An insect is rather limited in size, its body, and it's due to the structure of the insect. Now, all insects breathe through little holes in their abdomen, and so, I can't draw worth beans, but suppose this is an insect, and insects do have 6 legs. All right, so there's these little holes after the thorax in it, and I think they're called spiracles, but I could be wrong about that term. And it's kind of a primitive respiratory system. They suck in air through these little holes, and somehow in their body the oxygen is taken out and utilized. And they don't have lungs like we do, but they have some kind of system that extracts the oxygen and does that. Now, if you were to somehow were able to snap your fingers and make a much bigger insect, as the insect is made bigger, its weight increases according to the cube, the third power. But the amount of air it takes in, the air is being pulled in across an area. So the area affects how much air can be brought in, but the amount of oxygen needed is dictated by the volume. And so, for example, if you had an insect that was 10 times as long, and it would have 100 times the area, 10 squared, but 1,000 times the weight, 10 times 10 times 10, because again, the weight is a volume related measurement. It's length times width times height. The weight occupies that volume. So, an insect 10 times as long requires 100 times as much air. Can only breathe in 100 times as much air for 1,000 times its weight. So it's going to have a big problem breathing, and won't get enough oxygen. And there's a side issue on this. The size of the insects and these holes, the way they've been designed, protects them from drowning pretty well. I mean, you notice you can toss a bug onto water, and the bug will generally float and not drown. And it's because the little holes are small enough that the surface tension of the water won't allow the water to rush in. And so, but if it's bigger, the surface tension is going to be too small, and the water is going to rush in. Incidentally, a nice, fast way to kill an insect is to drop it into a pan of water with just a drop or two of dishwater, dish detergent. And I've done this with fleas, for example. I've gotten a bunch of fleas off my dog or my cat, and I just I have a pan of a little bit of soapy water nearby. I just scrape them off the flea comb and they go into the water and they just drop to the bottom and die. It's because the soap water cuts the surface tension, and then suddenly they're breathing in water, and so with the surface tension gone, they breathe in water, they drown very quickly. All right, so there's a problem, breathing. Now this would affect humans as well, and so a human that was 20 or 30 or 50 feet tall would have a really tough time breathing, because inside our lungs the air is being passed across membranes. The membranes are areas, and so your lung capacity is really dictated by the amount of surface area inside the lungs. And I'm not very good at anatomy, but I think there are lots of folds and curves in your lungs, which creates a lot of surface area, and that air just goes across these membranes, and the oxygen gets traded out of there by some process. And so our lung capacity is really dictated by area, considerably. So a very 20-foot tall person would be what, versus a 5-foot tall person. 20-foot tall person would be 4 times as tall, would require 16 times the amount of air, but would weigh 64 times as much. So I'm sorry, they could breathe in 16 times the air, but would require 64 times as much. And so they would have a very hard time breathing.